Welcome to the AI Research Roundup. I'm Alex. Today we're looking at a paper from the Hugging Face trending list, published on August 22, 2025, which was about 4 days ago. The standout result is that extending effective model depth with recurrence, memory, and test time compute scaling markedly boosts multi-step reasoning, with token-level chain of thought supervision reaching near-perfect accuracy above 99% up to 4 steps. The paper is titled Beyond Memorization, Extending Reasoning Depth with Recurrence, Memory, and Test Time Compute Scaling. And the implications for model training are quite significant. In short, the study shows depth matters far more than width, and methods like adaptive compute and reinforcement learning reliably push models to reason over longer horizons. Also, the authors shared a GitHub repo. It includes the associative recurrent memory transformer code, training and evaluation scripts, configs, and notebooks. You will find examples for language modeling and cellular automata, GRPO training utilities, datasets like Babylon, Hugging Face style runners, and clear install instructions with requirements. Alright, the intro laid out why extending effective depth matters. Figure 1 shows how the one-dimensional cellular automata benchmark encodes reasoning. A local 5-bit rule maps each position to the next state, which produces an orbit of binary rows over time. The panels illustrate rule tables, space-time patterns across width W equals 20, and the orbit-to-state task, where the first 10 rows form input. This setup forces models to infer the hidden rule and then apply it repeatedly, so multi-step prediction truly tests chained reasoning. So the setup just established the dataset and tasks. Figure 2 shows 3 panels that contrast single-step success with multi-step fragility. Panel A reports exact match for one-step prediction, where all models except LSTM reach above 95%. Panel B reports rule bit accuracy, which confirms most architectures infer the hidden Boolean rule, while ARMT lags. Panel C tracks GPT neox across lookahead steps, and accuracy plunges from near perfect at 1 step to below a quarter by step 3 and 4. Alright, the previous panel showed GPT neox struggling as lookahead steps increased. Figure 3 compares 2 levers and makes the contrast explicit. Panel A shows exact match climbing sharply with more layers, so K equals 2 improves a lot, and K equals 3 keeps rising up to about 12 layers, while K equals 4 stays low. Panel B shows widening the hidden size barely helps across horizons. The takeaway is clear. Depth drives multi-step accuracy, whereas width yields only modest gains. So, Figure 3 showed that depth, not width, drove the gains. Table 1 lists the shared hyperparameters that kept the comparisons fair across models. Each model used 4 layers with model dimension 128, while ARMT added a memory size of 32, and Mamba used a state size of 16. The maximum adaptive computation time iterations was capped at 4 for every architecture, which matters because equalizing this budget lets performance differences reflect architecture and recurrence rather than extra compute. Wrapping up, 2 takeaways stand out. Effective depth, not width, governs multi-step reasoning, and mechanisms that extend depth, like recurrence, memory, adaptive compute, and token-level chain of thought, reliably push lookahead horizons. The broader implication is practical. Training and inference should budget compute for iterative thinking. That is it for this episode of the AI Research Roundup. I am Alex. Thanks for listening.